Well, having covered the triangle inequality and the applications that will be relevant in the future and that we'll most use throughout the course, we turn to induction, which is one of the ways, one of the techniques for proving statements that we will use that were mentioned before. So this is a very common way of proving statements involving the natural numbers So remember then when we define sets, before, we talked about what a set was and the ways of presenting a set. One of the ways was to use a proposition, which is the most commonly used one. So basically, we have a set, so we want to show that we are given a set A, defined as a set of n n, so the sort of natural numbers such that a given proposition is true. P of n holds. So here to check that something holds for all the natural numbers, we must show that A is equal to n. So to show that the proposition P of n holds is true for all n in n, is equivalent to showing that A is equal to n. Why? Because that would mean that this proposition here, Pn, it's true for all the values of n here. And so the induction argument follows a scheme that actually can be adapted. So this is what we're going to present here is the most basic way of going about it, but in general you just need an algorithm that allows you to generate all the natural numbers starting from a base case and a certain rule that allows you to include more and more numbers until you cover all the natural numbers. So the principle principle can be stated as this. So we have a set S subset of the natural numbers satisfying two conditions. The first one is that 1 is in S. So the natural number 1 belongs to the set S. And if n belongs to S, then n plus 1 belongs to S as well. must be in fact n. This is how we can summarize things. So if we are able to prove that our set contains 1, and that if n is in there, then n plus 1 is in there, then what have we accomplished? So from I, 1 is in S. From 2I, since n equals 1 is in S, we conclude that n plus 1 equals 2 is in S. We keep going, and then from 2 again, and what we just deduced, since now we already know that 2 is in S, since n equals 2 is in S, then n plus 1, which is 2 plus 1, which is 3, is also in S. And we can continue like this forever. This is not a proof, this is just to show you how the argument works. I mean, the fact that this principle works is at the core of the definition of the natural numbers. So basically you can think of it as working because that's how you can define the natural numbers. But the idea is that, so that once you know that one element is in there, and then that means also that once you have an element there, the next one is also inside the set S, then you can generate all the natural numbers starting from the first element. So if you have that 1 is in S, it's in property I, and the second property, and in S implies n plus 1 is in S, then you get all the natural numbers. How does this apply to actual mathematical problems? You may remember some examples from Math 279. But in case you forgot, there's one very elementary example from the book. We'll see more sophisticated applications later in the course, and also for homework and in problem-solving sessions. But this is an elementary application. So we let x1 be equal to 1. This is the example 1.2.7. So let me just write it over here. So 1.2.7 from the book. They define x1 to be equal to 1, and for n in n, they define x of n plus 1. That's 1 over 2 times xn plus 1. We include colon here to indicate that this is a definition. Okay, so this notation here means that it's not just an equality or something that we can arrive making deductions from previously known statements. This is how it is because I wanted it to be this way. So n plus 1 is defined as 1/2 x of n plus 1. Okay, and then since we have defined x1 to be equal to 1, by induction again, proceeding the same way, we can deduce that, we can define the value of x sub 2 and then the value of x sub 3 and etc. And so they give, they compute what x1 is for a few examples. So let's compute it just like in the book. Compute x sub 2, which will be just 1/2 of x1 plus 1, but x1 was equal to 1, if you remember, plus 1, and this gives us 3/2. x3 will be 1/2 of x sub 2 now, plus 1, or 1/2 times 3/2 plus 1, and this is equal to 3/4 plus 1, which is equal to 7/4. Okay, and we can keep going. So we have a sequence of real numbers. Here there are rational numbers, because remember that we haven't defined what real numbers are yet. That will come next. And so what we want to show now is the following statement. That for every n, in n, x of n is less than or equal to x of n plus 1. Okay, so this is what we want to show. Okay, so just a little bit of notation. This is said to be a non-decreasing sequence. Okay, so if you have a sequence for which the values are not getting smaller, then it's a non-decreasing sequence. If the inequality was strict, then the sequence is called increasing. Okay, then in fact both statements are true in this particular case, but we're just going to follow the book, which only asks us to prove that the sequence is non-decreasing. Some people will actually call this increasing sequence, and when you have strict inequality, strictly increasing. This is just a matter of preference and the books you're using. Okay, but this is the statement we want to show. So for every n, x of n is less than or equal to x of n plus 1. We need to show then that the base case. So we want to show that this is true for n equals 1. For n equals 1, so we want to show that x of 1 is less than or equal to x of 2. But x of 1 is equal to 1. This is the definition here, up here, and x of 2, we computed it to be equal to 3 over 2. And this is less than or equal, and even less than 3 over 2, which is equal to x sub 2. So that means that the statement is true for n equals 1. Now, so this is the first step. So we need to prove two things here when we're dealing with induction. The second one being that if one number is in the set of numbers where this proposition is true, then the next one is in there as well. So this is usually denoted by n plus n plus 1 part of the argument. Okay, so we assume now, that for some n, x of n is less than or equal to x plus 1. And we want to show that xn plus 1 is then less than or equal to x of n plus 2. Okay, so this we know, we're assuming. No, so we can use that. And this is what we want to prove. Okay, so we assume the first statement, and we want to show then that the second statement is true. But, in fact, this is true because x of n plus 1, by definition, is 1/2 of xn plus 1. And this, in turn, is less than or equal to 1/2 of x of n plus 1 because of the end case, the assumption, the hypothesis of the end case. And we're adding 1 on both sides, but this happens to be equal to x of n plus 2. Okay, so this is the and so we've accomplished showing that if x of n is less than or equal to x of n plus 1, then x of n plus 1 is less than or equal to x sub n plus 2, which is what we wanted. Right? And it's all in here. So here in this inequality, we use the induction hypothesis, because we're comparing x sub n and x sub n plus 1. Okay, so this is just one instance of the use of induction in proving statements involving natural numbers.